see really nice bubbles. This is the steam rising from the ice, and it has nowhere to go but through the lava. And at the front of our lava flow, there's no bubbles because there's no ice there. So soon the lava will reach the bottom of our slide already. And I will show you some lava formations, starting with Pele's hair. Pele is the Hawaiian goddess of lava, and this is her hair. So in nature, this forms when lava falls over an edge and there's a bit of wind. And you can see it will create these very thin strands of lava, which cool very quickly, and it turns into something that looks like hair. You can see it cools very quickly. Our flow is getting bigger and bigger. In some areas you can see that the lava is already turning dark in color and doesn't seem to be moving so much anymore, like here on the top. And that is because the lava, which is exposed to the air, cools fastest and acts like an insulation layer for the lava below. So it doesn't look like it here, but there is still a lot of flowing lava under this lava here on the top, which is not moving. And we have proof of that here because it's still spilling out. So there you can see it's still flowing underneath this layer, which doesn't move anymore. At the end of our lava flow here, we have another lava formation, these beautiful shapes here, this wavy pattern is called Erupted lava. This happens when a liquid layer of lava is moving under a layer of lava which has cooled already a little bit. It's kind of like warm milk or a hot chocolate. If you leave it, there's this little film, this little skin that will come on the top. And if you then move the mug again, the cup, then it will create this little ripple, wavy effect on it. It's the same with the lava. Same principle. I have some extra ice. Shall we put it on the lava, see what happens? Cool. Let's see. So of course in nature, when this happens, this is when you get an explosive eruption. Here on a small scale, it will just produce a lot of steam. So there will be a lot of steam and it will make some noise, but that's about it. But it will do something really cool to the lava, you will see. So steam is escaping also from under the lava, creating these bubbles on the back of the ice. You can see that the whole thing is inflating because there the lava has cooled so much already that it doesn't want to open to let the steam go through. So instead it's like a balloon that it inflates and it goes up and it creates a hollow space below the lava. And in the places where we have most ice and most water, the lava cools fastest and it turns dark. So here you see, I can tap on it and it's already very hard, even though it was liquid just a few minutes ago. So the ice will continue to melt a little bit. You can hear crackling noise. This crackling is the lava which is shrinking. It creates small fractures that then meet each other and create bigger fractures. And that's why this whole piece, if we leave it like this, it will break up in smaller pieces on its own while it is cooling and shrinking. And you will continue to hear this cracking noise for quite a bit. So we don't have any moving lava anymore. You can see dark lava, you can still see glowing lava. When it came out, the lava was 1100 degrees Celsius, 2000 degrees Fahrenheit. If it goes under 600 degrees Celsius, so half that temperature when it came out, it's not glowing anymore. So in places where it's still glowing, it's still warmer than 600 degrees, but you see it already lost a lot of its heat. This area has hardened enough already for me to put this metal rod under it and lift the whole thing. Puncture the bottom so I can show you how liquid it is inside. You see, it's mozzarella cheesy lava, so still very liquid and still very warm, and that's because the lava around it is acting like an insulation layer. And I'm scooping this lava out, and you will understand later in the show why. Okay, and we're gonna leave it like this for a little bit. And in the meantime, we can have a look at the front of our lava flow, where we have these beautiful bubbles. So we have this big one here, which is formed behind the ice, and you can see inside it's still glowing a lot. But you can also see that that layer is very, very thin. But even just that thin layer really helps trap the heat inside and keeps that lava, which is inside, maybe not liquid, but at least very warm. And since this layer is very thin, it's enough for me to just tap the bubble, to break it, you see? That was enough. And it's very warm inside, so if I put some paper in, it will ignite instantly. And I'll try to put it in, because then we can get a little lava lamp. So yeah, you see it's still very warm there. It's not even very comfortable for me to get close and stand there too long. So it's still really warm. If we leave it like this, our flow, it will be cooled down in 3 days. But if we have this in nature, a lava flow which is big, can take up more than 100 years to cool down fully. And during this whole process, the lava is shrinking and cracking like this, and so new fractures appear all the time while it's cooling. And that's why it's so dangerous to walk on fresh lava, because it's still cooling and fracturing in all kinds of places. It's very difficult to say where. And there's many empty spaces. So like here, for example, yeah, here, you see it's completely hollow on the inside. So there's like a roof, which is a very thin layer, and inside there's like a cave. And those cavities, they form a lot in nature, not because there's a crazy guy throwing ice on the lava, but because there's a lot of gases present in the lava that want to escape and go up. And it will be very large caves like this. And you see that the ceiling is very fragile. It doesn't take me much effort to break it. And in nature, the weight of a human body can easily be enough to trigger that fracture and have it collapse. And it can still be very, very, very warm inside, even years after that lava came there. And that's why you should never walk on a